All right. Recently I did a square root calculation with pencil and paper algorithm, the long division looking method. I've heard of it described as the Babylonian method, but I'm not entirely sure. I just know how to do it. I also know how to do it algebraically, but this time we're going to try to do it geometrically. So I'm going to start by constructing a golden rectangle. And I'm going to do this a bit differently than I've done the other one. So here's a little vesica piscis. This one's on its side instead of upright. I'm going to give a little line there. I'm going to draw another circle that's a bit wider around each one of those. And then I'm going to draw a line across the other direction. And I'm going to take a point. Well, I thought I was going to take a point in the middle. I might just have to take intersection point of the two big lines. All right, and I will also take intersection points of the two little circles. Great. Now, there is a method, as I said, for finding a square root graphically, geometrically, and we're going to do that. This square root method also finds a root, basically, of a square, which gives you the same area as a rectangle under analysis. All right, so at this point I'm going to go ahead and hide some of my construction lines. So we'll actually get rid of these two big lines, get rid of the big circles, get rid of the small circles if we can. Actually, I want to see that dot, but I don't want to see that circle. But it's not giving me the option of hiding that circle. Let's try again. That dot, oh, that circle now is somehow miraculously hidden by itself. And get rid of that dot, and I think we're good with that. So we're going to want then a perpendicular line. Well, it would help if I had left my horizontal line, but I guess I can get along without it. I'll put a line here, put a point there. Okay, and now I can hide these two lines as well. Well, that's not my line. There we go. All right, now I'll hide my square, but I'll keep my points visible. And there is our golden rectangle. We'll actually make it gold. All right, now super duper. We're going to, at this point, I'm going to take a circle and I'm going to put it on this corner here on the side, just like that. We'll minimize the line here. We'll make it a little lighter. Okay, and I can leave that circle there just like that. That'll be fine. We're going to want to, let's see, I'm going to want to unhide the horizontal line across the top of this. And that will allow me to do the intersection with that circle. Now, if you are drawing a circle with a compass, you're going to need to find a midpoint. You'd need to find a midpoint of this line, okay, somewhere right in here. And then you could draw your circle. You know how to find a midpoint. You put a couple of overlapping circles. They've got to be equal. Two circles of exactly the same size, so you make them without changing the compass setting. You set up the first one to go over halfway, and then you have the other one, and then you draw a line in between their intersection points. I don't want to spend all day doing this, so actually I don't even need to do that. I keep forgetting. Semicircle in GeoGebra is defined between 2 points, so there's a semicircle. Now I'm going to want a vertical line here. I'll copy the visual style of this light circle, and I will just sort of, well, let's see, I'm going to need to put a point up there, and then this is the actual length. That then would be the square root of phi. Now, how does this work? I don't know exactly. I can't tell you in deep detail, but I can tell you this. If you go to the ends of a semicircle, or if you draw any circle and you take its diameter and you take the end points of that diameter and draw them to any point on the circumference, from the two endpoints to any point on the circumference, you will get a 90-degree angle. If you take any triangle, any right triangle, and draw an altitude from the hypotenuse to the vertex of the 90-degree angle, you will get two similar right triangles. So that just sort of points to the idea that there is a relationship, proportionally between the two sides here. And you'll note that this length, also this length up here, is phi, and this length is 1, which is the same as this length, and we know that by virtue of the circle, because all points from the center of a circle to anywhere else on its circumference is an equal distance. Okay? Now, so we've got the square root of phi. Now, furthermore, this triangle, we've already got the triangle that we would want to build with this information. This is called Kepler's triangle, and its dimensions are 1, phi, and the square root of phi. It just so happens that this length is phi, equal to this length. This length, of course, is 1, and then this length is the square root of phi. Okay? Now, just taking that triangle, I happened upon this as a method of solving a problem, which was I was searching for a lot of images of geometric figures, and I was trying to see if I could figure out how to duplicate them. And I came up with an image that had this triangle with its side lengths labeled, sitting over a square and a circle. And I said to myself, how am I going to construct this triangle? And I already knew pretty much how to do this. This is the Euclidean method for getting the square root of a length. So the general rule for this is that any if you have a unit, let's see, we just want to put a point here. It doesn't matter whether it's on the left side or the right side, but as long as the line under the semicircle is divided into 1 and any other number, then that vertical line from that division point between 1 and any other number gives you the square root of that any other number. So just imagine that that's 1. Now, there's a couple of different ways you can think about doing this. You can think, well, if you were working with a rectangle underneath here, every amount of height that you give the rectangle is sort of taken from its width, right? And if you imagine just using larger and larger numbers, then it increases but slowly. And here's an interesting idea. So we'll go all the way back to the very beginning of this. Now that would have to be a number less than 1, you understand, because if it were 1, then your triangles would be 45 and 45 and 90. So that looks about right. So I'm gonna just sort of assume that that's about right. So I'm gonna do another couple of perpendicular lines here. Perpendicular from that, and we'll just sort of lighten those. So I'll take, we'll really take these, and make them very, very light. Okay, and then I will put a point where they overlap, and I will look at the properties of that point. And one of the things you can do is you can trace a point. So this point is going to move along with the end of our circle, and it's also going to have its height determined by the height of this intersection point here. Okay, and so we're going to graph, essentially, whoops, what did I do? Let's undo that. Okay, so we're essentially going to graph the function of the square root of x. Not a big deal, but you know, we can do it, and we are going to do it. And here we go. Oh wait, that's not tracing. Why isn't that tracing? So trace on. Yeah, okay. Let's try that now. Oh, there we go. Yep, there it is. That sort of sideways parabolic curve. That is the function of the square root of x. Okay. Yeah. All right. I really wish I could have done a better and more exciting video. I really wish I could explain how the similar triangles give you the square root in better detail. But I think I've ended on a high note, so I'm just going to say over and out. Well, no, I'm not. I'm going to take a moment, and I'm just going to say one other thing, which is that there's a lot of different ways of getting a square root. You can get a square root by, you know, estimating and adjusting your estimate. Just simply take any number, take a guess of a number that you think might be the square root of the number you want, and even if it's way off, even if it's way off, right? You multiply by itself. And if you find out it's, you know, way off, you know, then bring it way down or way up, depending on what you need to do, you know. And as you continue to make refinements step by step, you will eventually come up with a decent approximation of your square root. Even the one that you get with a pencil and paper algorithm isn't going to be strictly accurate. You know, it's not going to be, you know, down to the it's not going to be right on the nose. You know, no matter how many digits you've got, it's never going to be right on the nose. Graphically, though, you know, you are going to get a square root that gives you a square of an appropriate size. So there's that to consider. You know, that you know, trying to note it in base 10 might not be the same thing as actually, you know, producing it, constructing it. You know, I keep seeming to, you know, find every excuse in the world not to say the word construct, when construct is obviously what I mean. But there you go. Also, obviously, this method isn't practical for extremely large numbers and, you know, things like that. But it gets the job done. You know, so there's other ways of you can guess, and you can multiply and revise your guess. You can divide the number back into itself, which, you know, frankly, when you have like a long digit number after the decimal point, I mean, that just doesn't seem practical to me after step 2. There are certain algebraic formulas that you can get. I mean, you can try to take a wild guess at how far, like as a fractional amount, your square root is between, you know, any two numbers that produce perfect squares in the neighborhood of the one that you want. There's an algebraic formula that helps you with this, you know, and they usually come out fairly close. And one of the things, I mean, you got to think also of what you want to find the square root for, you know, and if you're framing a building, you know, if you're trying to, you know, get your wall to sit on a foundation, you're going to test that foundation. You're going to test the squareness of that wall by using the Pythagorean theorem. And how many digits past the decimal point are you going to be able to find marked on your tape measure? You know, that's an important thing to consider. But anyway, a square root is a real thing. It is a definite length. You know, it naturally occurs in certain places. You know, we could have done the square root of 2 this way as well. Anyway, now I'm getting towards 15 minutes. I feel like I'm getting way too long, so I'm going to stop there. Over and out.